Welcome back. So, we will continue the introduction part. So, yesterday we looked into the different design aspects. So, now we will talk about how to enhance the blast resistant design. So, we can work on the different aspects here. So, we can work into the material selection. So, traditionally we use concrete, steel and masonry, which are very common in blast resistant design, with each having a unique high strain rate profile. We can now have the design adjustment where we will have the strength increase due to the dynamic increase factor. So, this is a function of the strain rate effect. So, due to the strain rate effect, my inherent strength in this type of material increases. So, at high rate of loading, a phenomena that we call as dynamic increase factor, where the strength properties are increased. So, we need to adjust our material properties to reflect this behavior under blast condition. So, though the blast condition is a high rate event in which there is a more chances of failure, but we also gain in terms of the strength of the material. But there is a catch here, that though the strength of the material increases, there is a decrease in the ductility of the material. So, in order to do that, we need to incorporate different type of ductile materials, where we increase the energy absorption capacity of the system. So, ductile and tough materials have a signature that they absorb more energy and they reduce the risk of brittle failure during a blast event. So, ductile is especially important for elements expected to deform under blast loading. So, what we need to do is that we need to increase the energy absorption capacity of our structure and decrease the brittle disk failure. So, this type of things we can achieve using the smart material selection. So, here we look into the certain codes that are commonly used in the blast design example. Earlier there was a code called TM5-1300 issued by the US Department of Defense, but now it has been combined into UFC 33402, where all the three services have combined their research and formulated this code. Then we have FEMA code, FEMA 426, 427, 428, which gives us the guidelines for design of civilian infrastructures. Then we have AC SEI 5911 that talks about the blast protection of the buildings, and again the old code TM5-1300 is there. And I am very happy to also tell that we have an Indian code also, and the current version has also come. So, we will be discussing our Indian code also that deals with the blast resistance design. So, we are summarizing this thing, whatever we have learned till now in the introduction part, that blast loads are acting impulsively, they are not quasi-static. The effect of the blast loading is characterized by very high pressure duration occurring in a very low time. They pose very high catastrophic failures. The structure response depends upon its mass, stiffness and ductility. The reflected and internal blast pose serious threats to all types of infrastructural scenarios, be it military installation, be it civilian installations like hospitals, electrical installations, data centers, and till whatever research has been occurred covering UFC, FEMA, ASC and IS code, they give us some insight into how to design for this structure, but there is a long way to go, and there is a long way to incorporate the different type of performance based design, taking into account the response from the non-structural elements, given a holistic view depending upon the risk assessment, the risk mitigation effects. So, we have to go a very long way to properly issue a protective design codes against the blast event. So, the challenges remains in the uncertainty of the event, the cost associated with the design methods, and the complexity. The complexity does not only comes from the effect of one type of this event associated to any structure, but also the complexity from the interaction of the different multifaceted interaction of this extreme events, like when 2 or 3 extreme events are occurring simultaneously. Then how do we optimize the design, what type of design philosophy we have to follow, what type of performance objectives we have to face, especially when the performance objectives from one event is counteracting the performance objective from the other event. So, this type of things we have to holistically take into account and design for a proper blast loading system. So, now we move to impact load on structures. Now, we will be dealing with the impact loading that are occurring on my structures. In the first phase, we saw the effect of the blast loading on structures. Now, we are seeing the effect of the impact loading of the structures. So, in very plain sense, the impact loading can be summarized when a sudden application of force occur over a very short duration, which causes the stress waves to travel through the material. So, in the first case, an explosive was occurring. So, here there is a direct application of the force caused by some external agent. So, the curve that we see can be approximated by a Gaussian curve, where we see an elastic impact occurring on a structure. So, different types of examples of impact event can be a car crashing into another car, a car crashing into a barrier, missile punching the walls of the bunker. So, impact loading occurs in many engineering applications, and its analysis involves the complex phenomena of the interaction between the structure and the impactor, the large displacements associated with the impact event, the high strain rates, and the plastic deformations. So, all these phenomena makes the analysis of this impact event very complex. So, now we are trying to categorize and we are trying to associate some of the things where in a very simplest way the impact event is applied to a structure, and what are the different mathematical formulation that we use. So, if you look into the figure on the top right, we can see that this is an application of a force over time, and it is characterized by the mass of the impactor and the velocity of the impactor, and the impulse, the total impulse occurring is equal to the change in the momentum, and the area of the force deformation curve is called the impulse. And normally when we try to measure the change of force over time, for an impulse type of event, it can be characterized by a Gaussian event if the total events remains elastic. So, some of the things that we normally study is the impulse, that is the integration of the force time curve. So, from the Newton's second law, we can also characterize the impulse as the change in the final and initial momentum. So, in impact, what happens is that an enormous force acts on the body for a very short duration of time, producing a finite change in the body, which is also called as an impulsive force. The characteristic of the external applied load is called an impulsive force in case of impact event. So, laws of impact. So, a very simplified approximation of the impact event can be termed using the three laws. The laws of conservation of the momentum, the total momentum remains constant before and after impact. The laws of restitution, the coefficient of the restitution relating to the initial and final velocities, and the law of normal velocities, that is the velocities perpendicular to the normal remains unchanged. So, we give a very simple example of an impact event. Here the impact event is occurring against a rigid wall and it is a central impact. So, in first phase what happens is that the impactor approaches the structure and the impactor is in free fall towards the target. So, this is called the approach phase. Second phase is the loading phase, where the momentum of the impact, it is the moment of the impact where deformation occurs, that is my impactor has hit my target. Third phase is called unloading. This is the phase when the object begins to recover from the impact. It means that the impactor has left the contact from the target body. And the final stage is called the fly off. This is the final stage where the object rebounds away from the target. So, in the figure we can see the different phases associated with the impact. So, first phase we can see the approach phase. After that the loading phase occurs, that is the moment of the impact when the deformation occurs. Unloading, that is the reversal of the loading, and fly off, the impactor loses contact with the impacting body. The term central impact is used when the velocity of the center of the gravity of the impacting body moves along with the same line as the reaction of the impacted surface. So, this is a very simple example of an impact occurring on a rigid body. So, the key equations involved in this type of impact is coefficient of restitution, the impulse, and the loss of energy. When the velocities of rebound and impact are the same, the coefficient of restitution is 1 and there is no energy loss in the system. This is an ideal scenario and it is called a perfectly elastic impact, and in normal practice it cannot be attained. The other extreme of this event is that where it is a perfect plastic event for which the coefficient of restitution becomes 0 and the total kinetic energy is lost. So, we are discussing about this central impact because this is a foundational scenario illustrating energy transfer and loss which occurs during an impact. The coefficient of restitution also gives rise to a very delicate application in structural scenarios also. In a scenario where we want to perform an NDT, that is a non-destructive testing, we use the concept of coefficient of restitution, where we measure the number of times a impactor hits a given surface, and the more number of times the impactor keep on hitting a surface will gives a measure of the properties of the system. So, this simple impact phenomena using its simplest factors like the coefficient of restitution has led to the development of an entire field of research known as the non-destructive testing. So, impact engineering itself has many applications in the structural field. Now, we will talk about the impact resistant structures. So, infrastructure functionality. So, we have to maintain the operational integrity of the critical infrastructural system. Even if an impact occurs, our critical component should be functional. Energy absorption, the structure should be designed to absorb and dissipate energy from a certain impact. So, this energy absorption phenomena, that is the backbone of the design of any transportation system, car, vans or anything. They have to be designed such that the car absorbs the most effect of the impact and the occupant does not sustain any severe injury. So, energy absorption becomes a very critical component when we are dealing with an impact event. Occupant protection. So, ensuring the safety of the people inside structures during impact, as I already told, during a car crash becomes of a paramount nature. The catastrophic failure prevention should always happen. So, we always have to design our structure so that the structural collapses under extreme conditions. In normal condition, there is no collapse in the structure. So, functionality, energy absorption, occupant protection and catastrophic failure preventions are the 4 pillars on which the entire concept of the design against impact rests. So, applications of impact resistant structures. Impact resistant structures have found application in industry where guarding machinery and storage facilities are concerned, aerospace, protecting the aircraft and satellite from debris impact, from bird impact or any other type of hail or any other type of impacts. Military applications like protective armors, shelter for defense, bunkers, missile protection shelters. Construction industries where the important buildings like data storage centers and barriers, rockfall structures are being designed. In automotive structures, the impact study is taken into account so that the vehicles have an enhanced safety factor and they absorb most of the impact energy. Now, we deal with the design principles associated with the energy absorption. So, structure must absorb kinetic energy to prevent failure due to an impact. A key principle is that we have to maximize the energy absorption. This can be achieved through controlled deformation, allowing the structure to dissipate energy safely. For example, if we use a honeycomb type of structure, then we can control the deformation that is occurring in a structure, and this philosophy is being adopted into high speed trains and recently also in many type of car applications also. So, the plastic deformation is allowed, micro cracking is prevented and any pull out or fiber pull out type of deformation is being tried to be incorporated. So, there is no wear and tear of the structure itself. After that comes the material selection parts. The ductile material has to be selected. The most commonly used ductile materials are steel and aluminum that are used in the automotive sectors, that are used in the aerospace sectors, and that are also used as in sacrificial elements wherever we are dealing with the protection from the bunkers, for protection in the buildings. So, they serve as a sacrificial sheet and the inside structure remains unhindered. After the development of the composites, different types of composites have come into picture which are extremely light and have extremely good energy absorption capacities. For example, carbon fiber and glass fiber sheets are example of such composites where they have lightweight also and they are very good in absorbing energy also. There has been tremendous research into the field of impact resistant plastics also, such as polycarbonates and ABS systems are example of high impact resisting elements, and they can withstand sudden loads without having major plastic deformations. So, the material needs to be chosen very wisely when the impact resistant structures are being designed. So, the challenges in impact resistant design. The challenges in any type of design always comes between the parity between the cost associated and the protection that we try to achieve. So, same is the case in the impact resistant design also, where we have to balance the weight, we have to balance the cost, we have to balance the manufacturability in the design also. So, balancing weight, cost and manufacturability becomes one of the key concerns. All these things needs to be tested and the complex failure mechanism needs to be predicted, and a long term durability needs to be ensured. For example, in case of aerospace industries or in case of in case of automotive industries, any system will have to endure different type of impact events repeatedly throughout their life. So, a long term durability also becomes of the paramount concern. So, overcoming impact resistant design challenges. First of all comes the weight optimization. So, this is a key component in automotive and aerospace industries. So, there is a need to reduce material without compromising efficacy of the materials involved. After that comes, secondly, the cost reduction comes, where the economical material and efficient process have to be ensured. Thirdly, manufacturability focus has to be given, so that the simplified geometry can be manufactured, and this can be used for the mass production of different type of components, so that large number of components can be manufactured. For example, in case of missiles or in case of aeroplanes, in case of cars. So, the manufacturability plays a vital role. Failure prediction. In case of an impact, the localized failure, the different type of behavior of material under high strain rate has to be tested, understood, and it has to be incorporated in the design. So, we need to simulate the impacts for the identification of these weak points. Durability aspect has to be ensured, because all these type of structures go under repeated damage or repeated impacts throughout their life, and they have to be able to withstand this type of impact throughout their life. So, there is a need of rigorous testing to ensure the longevity of the structures. After that, we come into the simulation aspect of the blast and impact loading on the structures. Why do we need to simulate? In an ideal scenario, what should happen is that we should be able to test each and every aspect, and we should be able to calculate, or we should be able to monitor and record all the different parameters like strain, strain rate, stresses, deformations, and we should be able to do this over a very wide range of materials and over a wide range of samples. But any testing involves high cost, high setup cost, high cost for the material itself, because the cost of the material might be very large and that material might not be available in abundance. So, and all the parameters like stated above, like strain, strain rate, stresses cannot be monitored to that precise effect in each and every testing, and the number of testing that needs to be covered over different material scenarios is also restricted. So, to overcome all these limitations, the need for simulation was felt and different type of simulation practices were developed. one of the main simulation factors that is being used nowadays is using finite element methods or finite difference method. So, we will be now dealing, and we will try to iterate what are these methods and how they are used. So, as I said earlier, the safety, the physical testing can be dangerous because we are dealing with extreme events. So, always testing in the blast and impact scenario can prove to be very dangerous, and the simulation avoids this type of risk. The simulation is cost effective, so the prototyping can be expensive, and the simulation reduces these expenses. Design optimization is achieved by the simulation method. Simulation allows rapid testing of multiple scenarios. We can always change the scenario, tweak it, optimize the thing and resimulate it. The complex physics. So, simulation is able to capture the nonlinearities in the material, the nonlinearities in the geometry, the contact phenomena, and it can monitor all the desired quantities in terms of stress, strain, deformation, everything without having to put up very costly measuring instruments. So, here we are showing the impact of a rigid missile on a concrete slab. So, this type of things can be easily simulated using the currently available finite element softwares. So, different type of finite element softwares that are used nowadays. One is LS-DYNA. So, LS-DYNA is an explicit multiphysics analysis software platform. The strength of this LS-DYNA lies in the simulation of the impact events and the vast range of material library that it has. So, it has a vast range of material library comprising of different type of concrete materials, different type of steel materials, soil materials. So, the material library is very vast here, and that is why the LS-DYNA is very much used in the field of blast and impact resistant design. Abacus explicit. So, this is also a very advanced finite element software where we can material the advanced materials in the simulating platform. We have COMSOL multiphysics. It is less used for the high strain rate problems. We have a very good platform in ANSYS Autodyne, where it is a specialized software for impact and blast simulations, and one good quality that has come into the recent years is that it can have the multiphysics simulation also. For example, the simulation of an underwater blast can be very easily done using ANSYS. Then the conventional softwares that are traditionally used in the impact field like PAM crash, radios. So, this has been long used in the automotive industries, and there are other open source softwares also that for example, CalculiX and other impact open source software that are used. But the problem with the open source software is that the amount of help file, the amount of tutorial is less as compared to the any other commercially available softwares. So, we will have to put our own effort into debugging, into writing the programs or getting any type of tweaking in the open source softwares. So, it is up to the user to choose any one of the best softwares from here and do the blast or impact simulation as he finds fit. So, the fundamental of finite element simulation. First of all, we should be able to apply the blast loading or the impact loading. From the real world, we will have to mathematically transform the effect of the blast loading or the impact loading into the finite element world. After that, there should be an expressive time integration scheme. It should take into account the high strain rate, it should take into account the large deformation, and the failure modeling should be accurate. So, in finite element simulation, there is something called a garbage in, garbage out terminology. It means that if we give it incorrect options, it will do something and it will give us some results which might be incorrect. So, in order to achieve correct and accurate response, we need to give the material properties properly. It should be able to capture the deformations, the failure mechanisms properly, and it should be able to do a proper finite element analysis depending upon the time integration schemes and the other factors. It should be able to discretize the elements properly. The mesh density should be properly maintained. The numerical solution should be robust and the solution algorithm should be well tested. So, a very good finite element software should have all these characteristics to give us an accurate blast or impact analysis thing. Otherwise, we will enter something and that will have no validation or accuracy of the results in the real world scenario. So, which modeling? So, there are many modeling approaches which are used in the finite element simulation. There is a Lagrangian approach. So, Lagrangian approach is traditionally suitable for solid mechanics, but it may struggle when the large deformation comes into picture. There is an Eulerian approach. So, Eulerian approach is ideal for fluid dynamics with fixed mesh, and this is good for large flows. There is a combined arbitrary Lagrangian Eulerian approach which combines the benefit of both Lagrangian and Eulerian approach, and most of the time this ALE approach is used in case of blast or impact simulation. There is a SPH approach, that is the smooth particle hydrodynamics approach. So, this is traditionally used when the fragmentation and or meshless simulation occurs. So, here on the right hand side we can see a column element when this is subjected to a blast loading, and we can see the entire plastic strain that is being experienced by this column when subjected to a blast loading. So, we also give an overview of the high strain rate problem. So, there are different material models associated with each type of elements. For example, foams are there, where the foams has been modeled using a crushable foam model to maximize the energy absorption. So, this type of material models are also available in the finite element software. Then comes the composites. So, Hashing criteria and progressive damage models for composites have been developed, and they are being accurately applied in the composite material models, so that the overall behavior of the composites can be mimicked. Concrete, this is the most tricky material that is being used, because concrete itself is a very heterogeneous type of material, and different type of material models like Drucker-Pager, KC models have been used, but they are continuously being updated, and still the concrete material modeling is not, I would say, in a very mature stage, but what we try to do is that we try to test in the laboratory and try to put this material characteristic in the concrete and update it always, so that we have a very accurate representation of the concrete material models. Material models are understood to a better extent than the concrete material models like Johnson-Cook, Copper-Siemens models. They also incorporate the rate dependency and the plasticity effect, and they are very properly utilized in the modeling of this type of metals. So, other material models are there for soil also. Other material models are there for different components, different human components also. So, if we open any finite element software, we will see a wide plethora of materials that are being used nowadays. So, accuracy challenge in the simulation. So, the simulation has to mimic the real world scenario. So, whenever we do a simulation, we always try to validate with a real life case scenario. So, there are different aspects that plays into this accuracy thing. One is the mesh sensitivity. So, we have to refine our mesh so that we achieve a proper answer, a properly accurate answer. But what will happen is that if we make our mesh very fine, then what will happen is that the total amount of time required to simulate the entire thing will go very high. So, there is always a balancing act between the mesh refinement and the computational expenses that we incur for the accuracy. To achieve a good mesh sensitivity is a key factor in any finite element simulation. Then comes the case of contact algorithm. We have seen that the blast and impact are very much dependent upon the contact algorithms associated between the impactor and the target body. So, problems like penetration, overshooting error, errors in the impact simulations are the Achilles heel. So, they should be properly incorporated into the finite element simulation. Material calibration, as I was telling about the concrete part. So, there is always a need for a continuous refinement of the material properties. As we test and see the material properties in high strain loading under different blast or impact scenarios, we need to continuously update the material models. So, we have a limited high strain rate data testing facility. So, this also shows up in the material models. So, as we are increasing the capacity to test the materials accurately in high strain rate loadings. Our material models are becoming more and more accurate, but there is still a wide part to go, so that before we achieve a proper material model. So calibration again plays a big part here. After we have achieved all those things, there is always a necessity for validation against experiments to ensure the reliability of the finite element what we have simulated. So to sum up the challenges in finite element simulations, it has a high computational cost. It is multi-physics coupling when the phenomena like blast occurring in water is being simulated. There is a very restricted material data which needs to be further analyzed, tested, and it needs to be calibrated. Accurate modeling of the failure mechanism is required. So taking into aspect of all these challenges, still we have to do the simulation because it is very cost effective solution, and it is also very fast as compared to setting up of an experiment. So always we have to set up a parity between the finite element simulation and the actual experiments that we need to do in order to simulate our, in order to design our systems. So finite element simulations are of a great help, but they needs to be done in conjugation with the experiments also. So this was the overview of the entire course that we will be covering through our 12 weeks. I hope we will enjoy the course together, and we have given you a overview of the different things that we will come to see in the coming weeks. So we'll start the detailed explanations from the next class. Thank you.